Hi, thanks for joining me. My name is Connor McGarr, and today I will be giving a talk titled From Jump ESP to CET, the Current State of Exploit Development. So, brief overview of this talk, we'll go over the obligatory who am I, why we care about binary exploitation, vulnerability classes, exploit mitigations, the future of exploitation, and the lingering question that this talk hopefully addresses: is vulnerability research still practical for red teams and non-research firms? So, who am I? As I said, my name is Connor McGarr. I am an associate red team consultant at CrowdStrike, primarily client-facing. I'm interested in anything low-level, Windows internals, exploit development. If it involves a debugger, pretty much count me in. I have a Twitter. I also have a little, just a little personal blog where I like to post anything exploit development related, just kind of to share my passion. Additionally, I am a contributor to the CrowdStrike Red Team blog. So why do we care about binary exploitation, and what does this talk aim to address? So exploit development, the way that we will define it in this talk, is essentially memory corruption vulnerabilities. So we have a piece of compiled code, it has some vulnerability within it, and we look to take advantage of that to corrupt memory and force the program to do something it wasn't intended to do. These types of exploits are generally point and shoot, which means that we develop the exploit, we identify the target, we send it to the target, end of the story. Often these are remote, and when it comes to remote exploitation, often this is unauthenticated. Some cons to this type of exploitation: definitely mitigations hurt the portability of exploits, as we'll see. The cost and time to develop these exploits to be portable across various systems and work as expected. And it often involves a little bit of research and some lower level knowledge. So at one point in time, many moons ago, red team toolkits contained many binary exploits. A variety of software was written across multiple systems. There wasn't really a software monopoly in any of the different types of software that are out there. So you had many different vendors, not to say that there aren't many vendors now, but many different vendors, many different types of software, no real good documentation. The software development lifecycle never really took into security as much as it should have. And so this resulted in vulnerabilities in many pieces of software. You can see this through the old Millworm sites, the exploit database, a lot of stack overflows, which are very common, which basically before mitigations, find a stack allocation, overflow it, find the return address, overwrite it with precision, and then pass like a jump ESP instruction and jump to your shellcode, which would be on the stack, and then profit. This is no longer the case. Red teams really place a lot more focus on malware development, which I like to view malware development as a continuation of binary exploitation. You get to get the end result of a lot of binary exploitation without the need for all of the primitives that we will talk about in this talk. And you don't need social engineering. So that's kind of the outline. We'll try to address the question out. Is the price of getting involved with exploit development and learning about it, is it still worth it? Let's find out. Vulnerability classes. What are these? These are the ways essentially that an exploit is delivered, the actual contents of the exploit. This could be through like a stack overflow, as we explained, use after free, which basically you have an object on the heap. You find a way to free that object, but you still maintain a reference or handle to it. You replace that freed object with your own, and then utilize the old handle to execute it. You have a type confusion, which basically based on how different data structures and types are laid out in memory. One data type might be referenced as another data type due to casting or some other developer error, and you get an unexpected result because of just the way that data types are laid out. Some types need more memory than others. Some types use less memory. It just all depends. Arbitrary writes, very generic, often the result of another vulnerability class, but that doesn't have to be the case. Basically, just the ability to arbitrarily write data to a location, controlled or uncontrolled. These types of vulnerabilities are located in kernel mode and user mode. In kernel mode, you typically see a lot more stack overflows and more trivial, quote unquote, vulnerability classes, just because a lot of third parties know that it's complex to get a kernel mode driver developed, and they just get it working. They may miss security components of the development lifecycle. That's not to say that very complex vulnerability classes and chains aren't involved in kernel mode. That's just what I've experienced in my short time in this field. Additionally, user mode code contains a lot more documentation when it comes to security. In exploitation, a lot of the time you're going to have these exploit chains that involve like use after freeze or type confusions. But at the end of the day, any of these vulnerability classes can be found in anything, user mode or kernel mode. User mode exploits, basically that's your beachhead to get on to a system. So that's your initial access. But what do we do with that initial access? So if we exploit a browser, for instance, our beachhead access is going to be in context of a very underprivileged user because it's sandboxed. So we would need to leverage an additional exploit, a kernel exploit, for privilege escalation purposes. So that's kind of that local remote exploit chain where get access with the user mode exploit that gives you low privilege, escalate privileges. But in some cases, kernel mode exploits can be exploited remotely. You see this with things like Eternal Blue, SMB Ghost, or other exploits where the protocol has some interaction with the kernel or is completely handled in the kernel. So here would be an example video that we'll see of a local remote exploit chain. So basically we have a vulnerable piece of software running that's listening for network connections. All mitigations disabled, just kind of as a proof of concept. And then we have a vulnerable kernel mode driver. So the pros of this, as we'll see, we're 2 exploits away from remote unauthenticated system privileges. And we didn't have to phish anybody, social engineer, make social engineer calls, that type of thing. The cons, so it would be timely to develop an exploit, 2 exploits like this that work portably across many systems of Windows, essentially. And when mitigations come into play, you run the risk of exploit chains being broken. So as we'll see going on, mitigations definitely make exploitation less trivial, as the exploitation we'll see here. So as we see, we start a handler, we exploit the system with a user mode exploit, that easy with a Python script. Then what we do at this point is we use our ability to upload with a interpreter shell the kernel exploit to the victim system. So as you can see, the server username, we are the user anon, which is a low privileged user in this context. And then now that we have uploaded the kernel exploit, just as easy as executing it, who am I? And we are system. So it's that straightforward for the local remote. And that's why I'm giving this talk about exploitation, because is the price for developing those 2 exploits worth it? Because it was very quick for us to go from remote access to system shell. So that's what we'll be addressing. As I said, the lack of mitigations makes the exploitation just shown more trivial. So what happens when more roadblocks are added, such as mitigations? Exploit mitigations, and what are they? So exploit mitigations basically are operating system features that are either hardware enforced or software enforced that basically look to break popular exploit methodologies or chains, or just to get rid of the vulnerability class altogether. Modern systems like Windows 10 have a lot of mitigations that users aren't even aware of, even some of them having lower overhead, as we'll see, to the overall end user experience. But the problem is getting third-party developers to enable these mitigations for their applications. So that increases the threat landscape for all software. So let's talk about the first one, data execution prevention, DEP. This is documented very well in research and just in general. So nothing groundbreaking here, but it's one of the first mitigations put in place, and it's something all of us as vulnerability researchers have to take into consideration. Basically, it places boundaries between code segments and data segments, so memory is not both writable and executable at the same time. So you have portions of memory that are meant for executing code, and you have portions of memory that are just there to hold data. So if you try to execute code in non-executable portions of memory, you're going to get an access violation and your process will crash. So generally, what would happen with a Stack Overflow, for instance, is we would overwrite the contents of the stack, and then we would try to execute shellcode off of the stack. Well, the stack is a place where data is held. So if it's a data segment of memory, now with DEP enabled, we cannot execute code there. So code versus data segments. So we just kind of got into this in the last slide. If you look at these 3 screenshots below, in the left-hand side, we see that there is a call to CS:write process memory. So essentially, write process memory, when it gets loaded into the instruction pointer, it's going to start executing the executable instructions that make up that function, which can be seen in the middle photo image below, where we have move RSP into RAX and these different instructions that will execute. So basically, the code segment just refers to the part of the portable executable where the executable instructions are, which is generally the .text section. And as we can see here, these executable instructions are execute and read and do not have write permissions. Data segments. Data segments refer to memory that are used for things like variables, to hold return addresses, strings, that sort of thing. So the stack is an example of one of those data segments. So if we look at the image below, when we try to interpret the stack as code, we get these illegal instructions. This is because it wasn't meant to be interpreted as code. It's meant to be interpreted as data. So if we look at the next slide, we see that when we interpret the stack as data, things make much more sense. We have valid addresses. These are where return addresses, stack allocations, variables, those types of things would be located here. What was the point of explaining all that? Why do we need to know the difference? Because technically the way that DEP works is it doesn't allow code execution in data portions of memory. So now that we've learned the stack, for instance, is the data portion of memory, if code was put there, we cannot execute it with DEP enabled. So Stack Overflows, at this point, we cannot exploit. DEP additionally also has support in the kernel. So on Windows 7, the default kernel mode allocation was non-page pool, which basically the non-page pool is memory that is always backed by physical memory, but it was executable. So kernel mode memory was just executable. That's not the case now, since Windows 8, you have non-paged pool NX, which the NX stands for no execute, which is the no execute bit, which is DEP essentially. So what happens is DEP is enforced in the kernel through page table entries. This is for user mode pages and kernel mode pages. It's managed here by a bit in the kernel. So let's come up with a scenario. So let's say we have a vulnerability where we can write to the stack, whether that's a Stack Overflow or some kind of vulnerability class that allows us to perform a stack pivot. Before DEP, basically we would just identify the return address, override it with a jump to our shellcode, and then we are good to go. With DEP, we can no longer do that. So now that we know that we can't put code on the stack, how do we overcome this? We can take advantage of the fact that stack interprets the contents as data, yes. The most common way to go about this is with a technique known as ROP, or return-oriented programming. So what is ROP? ROP is essentially a code reuse technique. So as I mentioned earlier, the .text section is generally where you're going to find the executable instructions for an application. So with ROP, basically, you can parse the portable executable to locate the text section or other executable sections where there's code and say, show me the existing code within this application. And then each set of code is going to have a pointer to it. It's managed by a memory address. So when the instruction pointer needs to execute that code, it is supplied with the address and memory of that code. Much like a jump ESP instruction is passed. You identify within the application where the jump ESP instruction exists and you pass it the pointer. Well, we can use the same concepts here. We can't execute our own code, but we can take existing code within the application and execute that. So I like to think ROP as this image below, where a lot of us had this, especially me, in school at a very young age, where essentially you'd have an assignment where the instructor would say, okay, I need you to spell out this sentence using only magazines. Well, it would be much easier to take a piece of paper and pencil and write out the sentence yourself. But we have to adhere to the instructor's rules. So we have to use what we're given and we have to make it work. And each student is going to have a different submission because they have different magazines and they may find things in different pages. I like to view ROP in that same regard, as not every ROP chain, which we'll get into what that is in a second, is going to look the same. And we just have to make do with what we have. So we can't supply our own code. We can use what's existing within the program, but we are bound to that. So terminology, a gadget is one instruction and all of these end with a return, and I'll kind of explain why that is in a second. Then we have a ROP chain, which is basically just a series of ROP gadgets. So these each end with return because we need to control the stack, as we can see as a caveat for ROP. Why do we need to control the stack? Well, the reason that is because each one of these ROP gadgets, because it ends in return, it will return back to the stack, pick up the next gadget, and execute it, because at a lower level, return takes the stack pointer and loads it into the instruction pointer. So if the next ROP gadget is located on the stack, when the return from the current ROP gadget executes, it will pick up whatever is located at the stack, which will be the next ROP gadget in line, pick it up and execute it. So as I mentioned, the caveat is you need stack control, and we're limited to the program's instruction set. We want to try to avoid Windows native DLLs due to Windows receiving many updates. Instructions change, instructions are added, things change very rapidly. So we like to try to stick to the application module. So that includes any specific DLLs to the application we're exploiting or the actual executable itself. So how do we bypass step with ROP? Well, let's take an example of a 64-bit machine with the fast call calling convention, which is the default calling convention for 64-bit machines, which we'll explain what that is here in a second. So here's an example ROP chain. So as we can see, we have what are seemingly random pop RCX, pop RDX, pop R8, pop R9. With the fast call calling convention, when you want to call a function, you use these registers in this exact order to pass the function arguments. So RCX contains the first parameter, RDX contains the second, R8 contains the third, R9 contains the fourth, and then after that, you move down to the stack at an offset of 20 hex and keep going from there. So from this example ROP gadget, what we're doing is pop will take the next value on the stack and place it into the corresponding register. So when we see pop RCX, it looks at the next value, which we can supply, which is an interesting property of ROP. So we can control values that go into registers, we just can't execute code with dep. So what we do is we set up a function call to something like virtual protect. Why virtual protect? Virtual protect can be used to manipulate the permissions of memory dynamically. So we know that our shellcode will be on the stack somewhere. We can write to it, we just can't execute. So what we do is we load our shellcode on the stack somewhere, and we pass arguments to the virtual protect function to take the location of our shellcode and change the memory permissions to read, write, and execute. That way, because it's located in a data segment like the stack, we can just change the permissions of the stack to executable and then execute that way. with the only caveat being we have to reuse existing code. So as you can see here would be examples of pointers in the app.dll. We would just find these pointers, place them on the stack, and then they would execute. So that's kind of how we would bypass DEP with ROP. So let's talk about another mitigation, address space layout randomization, ASLR. So basically the address space on the machine is randomized on a per boot basis. So here is an example in kernel mode, which is also supportive of ASLR, where NTOS kernel, the kernel on Windows, is the base address changes upon reboot, as we can see. So let's talk about how this coincides with DEP. So we bypass DEP with ROP by essentially getting pointers to existing instructions and passing them. Well, these pointers, as we know now because of ASLR, will be randomized each time the machine is booted. So knowing this, we're kind of stuck because we're in the state where we know we can bypass DEP, we just don't know how to do it dynamically because these pointers are randomized. So we need to bypass ASLR somehow. So how do we do that? What does that look like? So there are three main methods that are pretty well documented. You have utilizing application modules or an application that isn't compiled with ASLR. So this does exist definitely, but it's not as common as it once was. Definitely still exists. You could brute force the address space. This is feasible with 32-bit applications. Basically, if you have an application that starts a new thread or restarts the process every time it crashes, what you can do is you can brute force, because ASLR only kicks in on a per boot basis, not on a per application crashing and restarting basis. So you could keep crashing that application until you guess the right address, essentially. But on 64-bit systems, you're not going to be able to do this. Well, I don't want to say you can never do this, but it's definitely not feasible because of such a large address space. But the best way is information leaks. Basically, it's either the result of another vulnerability, such as an out of bounds read, which we'll take a look at, or just a generic information leak. So this is, you see this commonly with generic kernel information leaks, which most of them have been mitigated now. But you see this with like creating bitmaps because graphics being handled in the kernel and being able to leak kernel addresses, or in browsers by abusing the behavior of JavaScript is another common way. So let's take a look at an example of an out of bounds read. So basically we have an array of 5 unsigned long integers, which are 64-bit values. And as we can see in the printf statements, we're indexing the array at the 0th position and the 1st position. So in array terminology, that would index the first value and the second value because arrays start at an index of 0. But look at the last printf. We have indexing we are indexing it at -5. Well, we don't have a -5 value supplied, but there's no bounds checking here to say, hey, you cannot index anything before 0. So what happens if we do this here? Well, we get our first 2 intended values, which were those 64-bit values we supplied, but our last value is a 64-bit user mode address, which is very interesting. So in this situation, we have the ability to leak a 64-bit address seemingly within the process space, but it's just one address. How can this be leveraged to comprehensively bypass ASLR for our purposes? Well, an interesting thing is, even though memory is randomized, the distance between addresses stays the same on a per patch basis. So what this means is basically, if you take the base address of an application and where we leaked the address, the distance between those doesn't change. So information leak.exe may get loaded at another address, but that means that the address we leaked will get loaded at another address in such a way that the distance will remain the same. So it would be the same thing like if if the information leak.exe got loaded at 1 and the address got leaked at 2, maybe information leak loads at 3 next time, but the address leak loads at 4. That distance remains the same. So basically what we can do is if we find something within our application that gets leaked one address, we just need to calculate the distance to the base using a debugger. And then we know for that patch level the distance between those, and then we can dynamically resolve the base. And once you have the base address, it's pretty much game over for that patch level. I'll reiterate that again. Because once you have the base address, you can take your ROP gadgets that you find in memory from disassembling the application, calculate the distance from the base, and then you can dynamically resolve your ROP chain now. To make this even more portable, there's a little more work that will have to go into it. Some popular methods are like creating a signature. So if you know the opcodes that make up your ROP gadget and you have a read primitive, you could just keep dereferencing the process space until you find those opcodes. Do it that way. There's different ways, hashing, some crazy ways. But at minimum, you need to be able to resolve the base. So this is the main way that it's done. And then you can bypass DEP and ASLR with one leaked address with SAT control. So KASLR, same thing as user mode ASLR. You have these two APIs, enum device drivers and NT query system information. These can be used from user mode, called from user mode to get the starting load addresses of all of the drivers. With some caveats, the process it's invoked from must be that of medium integrity. So integrity levels, there's high, medium, low, pretty self-explanatory. When you exploit something like a browser, the user and that process is in context of a sandbox, which is a low integrity process. You cannot invoke such APIs from a low integrity process. So bypassing kernel address space layout randomization requires an information leak like we showed before. Whether that's generic or an out-of-bounds read. And this is really only effective against remote exploitation because of that. Because if we have access to the system locally, we can just invoke these APIs. So to bypass DEP and ASLR, you need a write vulnerability and a read vulnerability, essentially. So we're up to 2 vulnerabilities already. So you can kind of start to see a lot of these exploit chains require additional exploits. So we'll cover a few more mitigations here. That will make the plot thicken. Control flow guard. Support in user mode and kernel mode. Basically, before we get into what it is, we need to talk about exploitation a little more. So a lot of binary exploitation, not all, but a good amount, requires overriding a function pointer. So function pointer, pointer to a function. You overwrite that with like the address of shellcode instead of the pointer to the function. So then if you are able to invoke that function pointer, it's just going to jump to your shellcode instead because you overrode it. So as we can see here, for an example, we have the no CFG test application and the CFG test 1 function. That function points to another function called CFG test. So what happens here is the main function of this program calls CFG test 1. Well, CFG test 1 is just a pointer to CFG test. So when you call main, it calls CFG test 1, which then calls CFG test. So basically, as an adversary, if you could just overwrite what CFG test 1 points to, so instead of it pointing to CFG test, get it to point to like the shellcode's address, an allocation of shellcode, for instance, just by executing the main function, you're going to execute your shellcode. So that's not good. So how does control flow guard mitigate this? So basically with CFG enabled, can't do that. So indirect function calls like the one just shown, the targets are checked by CFG. So basically when you compile an application with CFG, it creates this bitmap of all of the functions that are protected by control flow guard. And these are known as the valid targets. So each time a valid target gets called like that arbitrarily with an indirect call, it first gets checked by a CFG function, which says, hey, is this function within the bitmap that we just created? If it is, you're fine, you can call it. If it's not, you can't call it, which this is a good method to mitigate this, because like a virtual alloc allocation is a dynamically allocated instance of memory. Well, that's not going to be part of the bitmap at runtime, or that gets created at compile time, because it doesn't exist because you haven't invoked the function. So you would crash at that point essentially. And you can use dump bin, which is a tool on Windows, to view all those protected functions. So here's how these functions look. So on the left-hand side, you have the function without CFG, and on the right-hand side, you have the function with CFG. So with CFG, as you can see, an additional function is called. That function is the guard dispatch iCall function, which does the checking, essentially say, hey, is the function that we loaded, that we've just preserved to inspect, is it a part of the bitmap? If it's not, you crash. So how do we bypass CFG? Well, an interesting thing is you could override a function pointer with another valid target. So CFG only looks to check if a function is within the CFG bitmap. So if you have multiple functions in a program that are all protected by the bitmap, you could overwrite each of those functions with each other and you'd be fine. Additionally, very interesting thing to note, so NTDLL and kernel32 DLL get loaded into the process space. Those also are a part of the CFG bitmap. So all of those exported functions, or the functions that those DLLs export, are a part of the bitmap. So you can still invoke virtual alloc, virtual protect, those types of things. You just need to figure out a way to control the function arguments. Even more of a good way to do it is override a return address. CFG only inspects forward control flow transfers, not returns or backwards. So call pushes a return address onto the stack. That way the function knows where to return execution back after it's done executing. CFG doesn't expect those return control flow transfers. So if you could override a return address on the stack, invoke that function that was going to call that return address, you'd bypass control flow guard, essentially. The only thing is you need to leak the location of the stack, which if you have a read vulnerability, you might be good to go, but it may involve a little more to leak the stack. So SMEP, supervisor mode execution prevention. What is it? So this is specifically for local kernel mode exploitation. So you've obtained access to a system as a low privileged user and you're local on the machine already. And this is hardware based. So this is how a typical local kernel mode exploitation occurs. You have a vulnerable function pointer sitting in kernel mode. You have the ability to override it. And then you have your shellcode sitting in user mode. This was allocated with like virtual alloc, for instance, with read, write, execute permissions. You override the function pointer with the address of your shellcode, and then execution redirects to user mode and will execute your shellcode even though in user mode in context of the kernel. So SMEP mitigates, well, let's get into this first. So why is this preferred? So we know that dep is enabled in kernel mode and user mode. So if we wrote our shellcode directly to kernel mode, we would have to bypass dep, which could involve return-oriented programming in the kernel, or other methods of bypassing it, let's say through page table entries, which we'll get to in a little bit. So because an adversary has local access to the machine, it's easier to just call an API like virtual alloc, which since we have access to the machine locally, we can invoke that function and then make kernel mode execution redirect to user mode, which will execute the code in context of the kernel. SMEP mitigates this actually, and what it does essentially is it says anytime kernel mode code redirects execution to user mode code, blue screen, crash. And the way this is implemented as a feature on the CPU is through something called a control register through the 20th bit. So if the 20th bit is set, SMEP is enabled. How was this done exactly though? So x86 based CPUs have this state known as the current privilege level. So basically the CPU is segmented in such a way where there's different privilege levels because you have things like different stacks, different state of the CPU registers that differ depending on if it's kernel mode code or user mode code. So a current privilege level of 3 refers to user mode. A CPL of 0 refers to kernel mode. When you hear the term ring 0, ring 3, this is what this refers to. Windows only uses ring 3 and ring 0. So basically at a little bit of a lower level, if CPL 0 executes CPL 3 code, system's going to crash. And this is checked by the code segment register. Bypassing SMEP. So basically we know it's enabled by the CR4 register, but it is enforced by a page table entry. What is a page table entry? Think of a page table entry as just an entry in memory that essentially defines various properties and permissions of a memory address. So like a page table entry could say, hey, for this memory address, it is writable, readable, executable, and this address has been accessed before, it's already been written to, and this page is either resides in user mode or kernel mode. That's the bit we want to take a look at, is the US bit. That defines if a page is either in user mode or kernel mode. So if you look at the image, the red box in the bottom right hand corner, that K represents kernel. So this page is a kernel mode page. So basically, using an arbitrary write and read primitive, you can identify the page table entry for your shellcode. You can identify that US bit, which will be set to user mode. You can corrupt that and make it become a supervisor mode page. So even though the page resides in user mode address space, it can be executed because it becomes, in the eyes of the memory manager, a kernel mode page. And Morten Schenk did a lot of the research for this, with abusing this functionality in more updated versions of Windows at a DEFCON talk that I highly recommend you check out. So to bypass SMEP, as I explained, here's a quick image of it. You have an allocation at B8000, which is our shellcode. Then essentially, upon execution of the arbitrary read-write primitive, that changes to a kernel mode page. So now SMEP won't trigger whenever we execute this because it views it as a kernel mode page, even though it's technically in user mode, which bypasses SMEP. So arbitrary code guard is the next mitigation that we will talk about. This is a user mode mitigation, although a mitigation we'll get to towards the end called HVCI is basically the kernel mode version of arbitrary code guard. So I like to view this as DEP on steroids. So basically with DEP, we know that we can't execute code in data portions of memory. However, we still know that we can change that with a technique called ROP. It allows us to change it. With arbitrary code guard enabled, that's not possible. So basically ACG makes memory immutable. The properties can't change. So if you have a page that's responsible for executing code, like in the text section, it's read and execute and cannot be changed to be writable. Data pages are read-write and they cannot be changed to be executable. On top of that, you can't generate any new code that is read-write or execute anyways. So basically, from an adversarial standpoint, you can't use ROP to dynamically change memory to read, write, execute, and you can't allocate memory, new executable memory. So how do we bypass this then if there's no way we can do anything about it? So you'd be right in saying there's really not a lot in terms of public documentation. There's a few nice bypasses for JIT engines, like in the Microsoft Edge, which were mitigated in like the Windows 10 RS4 build, because just-in-time engines basically convert bytecode into machine code at runtime for performance benefits. And basically, because that's the job of the JIT engine to compile code and execute it, it's constantly creating dynamically executable code. So it's kind of iffy with arbitrary code guard. Additionally, you could use data-only attacks, which basically you use ROP, which you can ROP with ACG enabled. The thing is, you just can't change the permissions of memory. So you could build a full payload in ROP without using a first stage payload in ROP to like do something like virtual protect. You could build the full payload in ROP, but obviously very expensive to build something entirely in ROP. So that's kind of where exploitation as a whole is right now in terms of mitigations that you commonly see. And now I want to talk about mitigations that have support, but they aren't super mainstream yet. So we'll talk about CET, control enforcement technology. Basically, this is a hardware-based control flow integrity solution. As we know, CFG doesn't protect against return addresses. We talked about that's a way to bypass it. Well, CET protects return addresses on something called a shadow stack. So it creates a copy of the stack, essentially, and each time a return happens, the in-scope return address gets compared with the preserved copy. If they don't match, they crash. You crash. This is hardware-based. CET also provides forward edge protection with indirect branch tracking, but Microsoft doesn't use this. It uses CFG and another thing called extended flow guard, which we'll get to at the end. Because it's already got existing infrastructure for forward edge calls, it's not going to use CET's indirect branch tracking. So here's kind of how this looks when you corrupt a return address and you get a mismatch. You get a control flow protection fault. Bypassing CET, there's just not much on it yet. You need proper hardware to test, and it's just recently got support. There's a few blogs out there, namely from Alex Anescu, that go over CET, but only time will tell what kind of bypasses actually get documented. So extended flow guard. This is an enhanced version of control flow guard. So basically with CFG, we know that it's a good mitigation. It really is. And you see vulnerabilities like SIG-RED, the new DNS vulnerability, where some proof of concepts have come out, but because it takes advantage of DNS.exe, that's a Microsoft binary that's compiled with CFG, and we just haven't seen any exploits for that yet because the only exploits that have been released are on versions of Windows that don't have DNS.exe compiled with control flow guard. So it is an effective mitigation. I truly believe that it is. The only issue is that with CFG, you can still call other functions that aren't the intended function. Example, any function exported by the bitmap. So XFG takes this a bit further. So it takes the function that is protected, it takes the data type of the function, its parameters and return values, and it creates a 55-bit hash, essentially, of that. And it places that 8 bytes above each function that's a part of the bitmap. So basically when XFG checks the function, it looks 8 bytes above the function, it takes that hash and it compares it to a hash that gets loaded into the R10 register or preserved essentially right before the function call happens. And we'll see an image of that next. So basically it compares the hashes, and if they don't match, you get a control flow access violation. So on the left-hand side, we can see the XFG test CFG function. If you look 8 bytes above it, which that -8 is there, you see that there is a hash. And then if we look at the image to the right, we see how the function looks in IDA. As you can see, the hashes match, except for that last bit. That last bit gets added on essentially a bit beyond the scope, but when you step through the actual dispatch, that bit gets added on. But technically these are identical hashes. So you see that the preserved hash gets stored in R10, and then the call is made to the dispatch function, which will check CFG test -8 to compare them. If the hashes doesn't match, the process crashes. So basically now you've taken CFG And you've made it even better, because what happens now is with CFG, we could call other functions in the bitmap, but now we can only call functions that are in the bitmap and are of the same data type, have the same amount of parameters, and return the same type of value. And this greatly decreases the threat landscape and the amount of functions that you can call. So bypassing XFG, obviously return addresses will still be a target. You could call an identical function. As we know, the Windows API, for instance, exposes a few duplicate functions that you may be able to leverage somehow. This is more far-fetched, but those 8 bytes above the function, let's say you overwrite a function pointer with shellcode. Well, it's going to check 8 bytes above your shellcode allocation for the hash that it thinks will be there. Well, by a stroke of luck, the 8 bytes above could be the hash. It's very, very, very unlikely, and this has been taken into consideration. But nonetheless, it's not impossible. It's not totally impossible. Or leveraging an arbitrary read. Basically, you could dereference, if you have an arbitrary read primitive, you could dereference the entire process space and look for 8 bytes that equal the in-scope XFG hash. Once you find that, if there's a function 8 bytes under that, you could use that. That probably won't bear any fruitful results, but nonetheless, it's still something that I thought of that could possibly be used. And then we have VBS and HVCI as the last mitigations we'll talk about. These are very powerful in my opinion. They're hypervisor based. So basically VBS manages normal resources on Windows from the hypervisor. So you have Windows running on top of the Hyper-V hypervisor, and they're segmented in something called virtual trust levels. So basically VTL 0 is like what the normal user sees, and then VTL 1 is the higher privileged resource, essentially, that manages things from manages VTL 0 resources from VTL 1. And then HVCI basically is the main component of virtualization-based security, which enables immutable bits that set virtual trust level 1 permissions on virtual trust level 0 pages. So basically, this mitigates the ability to manipulate page table entries because those permissions are managed from a higher trusted boundary. So you won't be able to do that. This mitigates that. Additionally, you can't allocate new read-write X memory in the kernel. Essentially, this is what Arbitrary Code Card does, but HVCI supports this in the kernel. Bypassing these, again, same with CET, a lot of unknowns. Data-only attacks seem like they would be a good possibility. ROP in the kernel, just don't do anything to change permissions. And then hypervisor exploitation as well, leveraging exploits within the hypervisor could be an avenue. So now that we've gone through this presentation, is vulnerability research still practical for red teams, non-research firms? As an optimist, I think so. We know that we require a lot of vulnerabilities for things like local remote exploit chains with a browser exploit. And it's more difficult than it was, definitely. But the thing that I look at is when you see something like Eternal Blue and how easy of a win that is on an engagement, yes, it's a common exploit, but someone took the time to develop it, number one. And number two, it's just an easy win. And it's a very high vulnerability because of the risk it poses. A remote, unauthenticated kernel exploit. So if you can find one of those, if there's someone on a red team that has an affinity for exploitation and takes the time to come up with something like that, that's definitely a plus to add to your toolkit. So I say staying curious with binary exploitation and keeping your skills sharp definitely is a plus, because there's always crossover with other things like malware development, which I said at the beginning of the talk, takes a lot of the binary exploitation concepts and removes the need for all of the primitives. So it can help increase value there as well. So I just want to say thank you again for attending my talk. Thanks to BSidesDayton for having me as a speaker, and I will see you all in the Q&A.
Well, thank you very much for giving that great talk. You have to pretend you hear all the big claps.
I do. I hear them.
So does anyone have any questions for Connor in the chat or in the voice channel?
I don't.
So I'm kind of curious how. Oh, is it just my mic? Hey, I've got a quick question.
Yep.
Am I audible?
Yep.
Yes.
So with, what was it, ACG? Arbitrary Code Guard, I think you called it. That's the first time I've heard about that. Oh, I am hearing myself come back on the stream. I'm confused by that. How exactly does that? How exactly does JIT work with that? Do you know any of those details? Do JIT engines just sorry, do JIT engines just disable that mitigation when they're built, or?
Well, so we can talk about Edge, for instance, where a vulnerability once was by Project Zero. So basically, JIT in Edge leverages an out-of-process JIT engine. So there's a Microsoft Edge content process, and there's a Microsoft Edge.exe, which the content process is obviously what you see, and then you have your JIT engine. So basically, the way that handles are obtained for the JIT engine to do work within the content process. You can read the blog to get more technical details. I'll spare them for brevity's sake, but essentially, you could migrate from the normal process to a non-JIT process that way, since it leverages an out-of-process compiler. So out-of-process compilation is a big thing that was mitigated with the Windows 10 RS4 build. But yeah, JIT definitely doesn't jive with Arbitrary Code Guard, and that's why it's definitely a big target. That's basically Arbitrary Code Guard is write XOR execute, right, or W XOR X. If you've heard of that mitigation on other
Yeah.
systems, that's what that is in Windows essentially.
Okay. So they completely just, so Edge itself is built with the renderer process, which is where you've got most of the code base running. And then they slim down just the JIT engine into its own little isolated space. That's pretty cool.
Yeah, I'm not sure how the code base is set up, just because Edge is, recently moved over to Chromium, so the Chakra is being deprecated, I believe. But yeah, it is pretty interesting to see, and you should definitely check out that Project Zero. It's by Ivan Fraktik, I think it is. He kind of talks about how handles are obtained and ways to basically migrate into a Edge process that doesn't have ACG enabled, which would be the JIT engine.
Awesome. Thanks for the recommendation.
Yep, no worries.